In this video, we're going to talk about electronic components. Specifically, we're going to cover diodes and transistors, simplified in a way that's easy to understand. So, solid-state components, we're going to be using the semiconductor material. Two common semiconductor materials are silicon and germanium. They're going to take that material and they're going to put it through what they call a doping process, which I'm convinced I've met some people that have gone through that process. With this material, as it goes through the doping process, it's either going to add additional electrons or take electrons away. So it's not going to change the material. It's still silicon or germanium before and after the doping process. If it adds additional electrons, it's going to be a more negative or the N-type material. If it removes some electrons, it's going to be a more positive material or a P-type material. A diode is going to act as a one-way check valve. I've heard it referred to as an electrical ratchet, but it's going to allow current to flow one direction. It's going to block current from flowing the opposite direction. Let's take a look at this check valve. If I have a fluid here, the path is closed, can't go through there. What I'm going to have to do is build up enough pressure to be able to lift that, overcome the spring tension, and now allow it to flow. Since we're dealing with electricity, our pressure is voltage, and that pressure is going to be 400 to 700 millivolts. Opens it up, and current can flow. If we go in this direction with it, if we start putting pressure here, that's only going to add to that spring tension, and you're going to block it from flowing. Now, if you start coming with higher and higher pressure, you can essentially deform this thing, break it, and you can get the flow going in the opposite direction. Which diodes, if you expose them to too high voltage, do the same thing. Because it is a 400 to 700 millivolt drop, that means the whole time that current is flowing through this solid state component, we're going to have a voltage drop, which means they generate heat. Got to be able to dissipate that heat or you're going to burn it up. Because there's two things that will destroy a solid state component. One is a voltage spike, two is heat. So lower right hand corner is three different ways that they draw the diode symbol. This one here, I've got the diode connected up, so you can see current is going to flow from left to right. This one right here is physically what they would look like. Cylindrical shape, a solid color with a band on one end, and that band is going to be on the cathode side or the negative side of the diode. So here we can see we have our positive materials. Over here we have our negative material, and because we don't have anything connected up to it, it's just sitting there like that. Lights off. I close the switch. I'm going to put a positive voltage right here. I have a positive material, and they're going to repel. Over here, I'm going to have a negative voltage, which I'll come back and talk about the negative voltage, and a negative material. They repel. As these push toward the inside, it's going to build up enough pressure to overcome that gap where these are bonded together. Again, that's going to be 400 to 700 millivolts to be able to do that. Close the diode, light comes on. Now, the negative voltage. I apply battery voltage over here, and so I've got my 12 volts. Let's say on this side, instead of 0 volts, let's say that I have 11 volts over here. 11 is 1 volt negative to 12. It's not actually a negative voltage. It just has to be a voltage less than the anode on the cathode side. So that's where we're going to get our negative. So again, 400 and 700 millivolts is enough pressure to close the diode and conduct. Here I've taken the diode, connected up in reverse bias, close the switch. I have a positive voltage, a negative material, and they're going to be attracted to each other. Over here, I have the negative voltage, positive material, and they're going to be attracted. And you see that widened the gap. That's how we're going to block the current from flowing in reverse bias. Now again, this is a simplified explanation. If you want a more technical one, read through the book, get the technical description of how this is going to work. Here's one that would be hooked up in a circuit. We have a relay over here on the right hand side. This is our electromagnet or our control side of the circuit. As we run current through that control side of the circuit, flips the switch. When we shut it off, this magnetic field collapses down, and as it collapses down, it's going to induce a voltage into itself. That's our voltage spike. That voltage spike can get, into dozens or even hundreds of volts. When you start getting up into the 50 plus volts, if that voltage goes over and makes its way to some transistors, it can actually damage the transistor or even destroy the transistor. So we get 50 volts in here, and what's going to happen is that voltage is going to go through this diode and right back to the source. So this electromagnet became the source of the voltage spike. Electricity took the easiest path, which was through the diode, and that voltage spike stayed right in here. So this diode, when we close this switch, we're going to have battery voltage there. It's hooked in reverse bias, so it's not part of the operation of the circuit, but it controls the voltage spike. To test a diode, grab your meter, make sure that your meter has this diode test position. When you put it in the diode test position, you're going to hook your red lead to the positive side of the diode, black lead to the negative side, or if it has that stripe on it, and that's forward bias. You should get a reading between 400 and 700 millivolts. Reverse the leads, it should read OL. So as long as you get a reading between 400 and 700 when you're in forward bias, OL when it's in reverse bias, diode's good, it ain't broke, don't fix it. So the first one we're going to talk about is a Zener diode, and you can see the symbol is very similar to the diodes, just those two extra little clicks on there. But what a Zener diode is going to do is it's going to work like a regular diode. However, it will allow current to flow in reverse bias if the voltage gets to above a certain level. That Zener diode is designed to close in reverse bias anywhere from like a half a volt up to a couple hundred volts. Depends on how they design it. But on this circuit that they're showing here, they have a gauge. And this gauge can be damaged if the voltage goes above, X number of volts. So this Zener diode is going to be set to a voltage less than that. If something happens and we get the voltage going higher than that, this Zener diode is going to conduct in reverse bias, and it's going to take the voltage down. And then as soon as the voltage comes down to a safe level, the Zener diode will open back up. So if you were to monitor the voltage there, doesn't matter what the voltage spike is, that Zener diode is going to never allow the voltage to go above that point. So there's another type of diode that's called an avalanche diode. It's going to do essentially the same thing. So the last diode we'll talk about is a light emitting diode. On the light emitting diode, this technology has jumped tremendously over the last 4 decades. I remember back in the 80s using the scan tool, and the scan tool had an LED display that if you were in the sunlight, you could not tell any of those LEDs were on. You actually had to shade it over to be able to see what was on there. Now you look at cars, headlights are made out of LEDs, brake, taillights, and they're very bright. Early on, the technology with the LEDs, they consumed a lot of energy for the amount of light they give off. Now they're very efficient, and you see those all over the place. If you go to test a light emitting diode, its voltage that it turns on is going to be much higher than the 0.4 to 0.7. So depending on what they've done with it. So if you want to test a diode, just basically, does it turn on or not? Now we're going to get to transistors. The transistors, we're going to have 2 types, NPN and a PNP transistor. So these are referred to as bipolar transistors. They have 3 legs on them, emitter, collector, and base. Looking at the one that I mistakenly put behind my image, and we have this light bulb wired up to the N material. For it to turn on, current's going to flow through the N material, through the P material, and then back through the N material. The reason they call it a bipolar is because the current is going to flow through both the negative and the positive material. The way this is going to work, it's going to be like a 3-terminal relay. So looking at the center image, we have voltage applied to here, and you'll see the voltage is for the switch side, and the voltage is used for the control side. On the control side, I have this switch to be able to turn it on. Once I turn it on, now current can flow and turn on our light. So this switch is going to be the base. And then this leg here will be our emitter. The load is going to be on the collector. So this is wired up just like this bottom image of our emitter, arrow pointing in towards the P material. Our base is the N material, and then the collector is the P material. The one on top up here is our NPN transistor, bottom one PNP. So here's the way the symbol is going to be drawn on the schematic, and this is the part that I need you to be able to recognize. Here's the symbol that we need to be able to recognize. So the one on the left is the NPN, the one on the right is the PNP. You can see the collector, emitter, base. So when you see this symbol, you're going to identify whether it's an NPN or a PNP by the arrow. So if the arrow is not pointing in, it's an NPN. If the arrow is pointing in permanently, it's a PNP. On an NPN, I have a positive material for the base, which means I need to go to positive voltage in order to turn this transistor on. If it's a PNP, we need to go to ground or to the negative in order to turn the transistor on. That's what I need you to be able to do, is recognize this symbol when you see a wiring diagram, identify which one is the leg, and whether you need to put a positive voltage or a negative voltage to that leg of the transistor. So far I've talked about a transistor as being like a relay. The reason the manufacturers are going to use the transistor instead of a relay is because they can turn on and off much faster. They don't wear out near as fast, and they're lighter. However, transistors will do something different that a relay can't do, and that is it'll act as an amplifier. Looking at these two charts over here on the right hand side, you'll see the top chart is going from 0.7 to 2.7 volts. The bottom chart is going from 0.6 to 12.6. What this is telling you is as you put a small voltage to the base, it will turn partway on. As you increase the voltage to the base, that transistor will turn on more and more until you have it all the way on. If your stereo has an amplifier, the heart of that amplifier is a transistor. The sound, when it's electricity, is a voltage. As they vary the voltage, the frequency, the amplitude, that's applied to the base. As you vary that voltage, you'll vary how much that transistor turns on, and so you can put a higher voltage to your speakers so everybody can enjoy your music. Transistor as an amplifier. Most of the transistors that are used are not bipolar transistors. They're actually a unipolar transistor, which I chose this particular drawing because on this one, we have our material, or our voltage is going to flow right down here through the center from the drain to the source. The drain was our now emitter, source is the collector, the gate is the base. They changed the names on you. But the current that's going to flow through there flows through either a P-type material or through an N-type material, not both. Hence the name of unipolar instead of bipolar. The way the base is going to work is as we apply a voltage or a ground, depending on whether it's a P or an N-type material, it's going to build up a magnetic field. And as this magnetic field builds up, it's going to shut off the current flow through there. We're using a magnetic field. The other name that you're going to hear, actually the more common name, is field effect transistor. And you've probably heard of that, but the way that you heard of it is a MOSFET, metal oxide semiconductor field effect transistor. Most of the transistors that are used are this style. However, on the wiring diagram, this is the symbol they're going to use, is one of these two, either the NPN or the PNP. That's why I need you to be able to identify these two symbols. The last type of transistor is going to be a phototransistor. And on a phototransistor, instead of using a voltage at the base or at the gate, we're going to apply light. So the more light that you expose to it, the more it's going to turn on. And you can see over here on the left-hand side, this is dashboard. It's right in the center of the dashboard. And as the sunlight hits this, it's going to record how much light, ambient light, there is. And this is going to be used for like your automatic headlights, or it is going to be used for your HVAC system. So the light that's coming through the windshield is going to heat up the interior, so your HVAC system is going to compensate for that. Now the last slide that we have here is integrated circuits. As they started building the solid-state components, they just had this little thing called a breadboard, and they would stick the individual components in there, make it do things. Now, as they started getting more and more complicated, the breadboard became bigger and bigger, and then they also found that the closer they got those components together, the faster it could work. They started integrating them all together to get our computer systems and circuit boards that we have today. Just to give you an idea of how far we've come, I put a picture up here of an Intel Core i7 processor. Physically, that's less than 38 millimeters square, and yet there's somewhere between 3 to 5 billion transistors that are on that. Hope this makes sense for you for what a diode is, how to test it, and a transistor and what a transistor does.